Hey everyone, welcome to Web3 for Developers, a channel for developers to learn about technologies in the blockchain space. Today, I'm going to talk about the OP stack. The OP stack is a roll-up stack created by Optimism. You might have heard of it because it's used by the likes of Base, Optimism themselves, for OP mainnet, WorldChain, and many other chains. Let's begin by breaking down the definition of the category that OP stack belongs to, which is roll-up stack, word by word. So roll-up. What is a roll-up? We defer to the authority on this subject matter, which is L2B. Roll-ups are layer 2s that post state commitments and data to Ethereum. State commitments, they're cryptographic summaries of data at the current time that ensures that it cannot be altered later on without changing the cryptographic summary. So it's a guarantee that that data was checkpointed or saved or existed at that time, and later on we can check against it knowing that it wasn't changed. Data here refers to L2 block data. The commitments are validated, this is part of security, on the layer 1 using validity proofs or fraud proofs with a challenge period. There should be no additional trust assumptions outside of the layer 1. So in other words, the layer 2 depends fully on the layer 1 for security and data availability. That is what a rollup is. Here, the distinction has to be made that the data availability, so if it's using a service like Celestia, that is considered as off-chain because off-chain is relative to the L1. So Celestia is not in Ethereum, that's off-chain DA. But still the state commitments have to be posted to the layer 1 because that's where the settlement happens and proving happens on the layer 1 as well. Now, even if the data availability is EigenDA, which is on Ethereum, it's still considered as off-chain DA and not a rollup because the data itself is not stored on Ethereum. On Ethereum, you could only have either call data or blobs, and then you're considered as a rollup because you use Ethereum fully, even for data availability. Layer 2s that use off-chain DAs can be referred to as either Validiums or Optimiums, depending on the proving system that they use. OP stack chains can be either rollups or non-rollups. This is officially supported because in the OP stack itself, there is Alt DA mode, which allows for the DA to be configurable. So you can have Celestia and use the OP stack without needing to fork the codebase. Now let's talk about the stack part of rollup stack. The list is not fixed. There can be new components, but primarily there are these components: OP node, OP batcher, OP proposer, which plays a different role now, which is less important than before, and OP geth. So OP node here is the consensus layer of the layer 2. It is responsible for the derivation pipeline, which we'll touch upon later, and it controls the execution layer when it comes to needing to process L1 transactions and also receiving the transactions from users on the layer 2. Between OP node and OP geth, and OP geth plays the execution role, there is the engine API, and this is the same as on layer 1 itself. OP batcher is responsible for posting the L2 blocks data to the DA layer. Proposer here, it used to post output routes. Well, I say used to, but it depends on the chain. So we have chains now that are using permissionless fault proofs, stage 1 OP stack chains like OP mainnet and Inc. And there's still chains that are not yet using permissionless fault proofs, and they are still using the OP proposer as the privileged actor that gets to post the L1 and say what is the L2 state at the moment. So OP stack components can be divided into layers: data availability, which is played by OP batcher, sequencing by OP node, derivation also OP node, execution by OP geth, settlement, security, validity, that is happening on the L1, and also off-chain there are Canon VM and OP challenger. Dispute game and MIPS, these are components on-chain. Governance, something that is used for upgrades and also fallbacks. As the system is still developing, sometimes you need the security council to intervene. And also, like I mentioned, there are new components. So there's now an OP deployer component that can be used to deploy OP stack chains that are compliant with superchain specifications. These components are modular. That means they can be swapped out for other parts. So SoonStack uses the OP stack, but they swap out OP-Guess. Instead of using the EVM, they use the SVM. So other rollup stacks that you might have heard of already are ZK Stack and Arbitrum Orbit and a bunch of other ones. So how does the rollup stack work? So on the layer 1, users can deposit, and on the layer 1 as well, when they want to do withdrawals, they prove and finalize their withdrawals. The derivation layer, taken care of by OP node and also OP-Guess executes it, takes care of the deriving of L2 state based on L1 state. So every L2 block has to be tied to an L1 block, and the L1 deposit transactions have to be included in the L2 block. On the layer 2, users can initiate withdrawals to return back to layer 1, and batching. This is done to send the batch data, L2 blocks data, to the DA layer. And again, even if the OP stack chain is not using Ethereum for DA, it would still need to post state commitments to the layer 1 so that proving can be done. Now, let's talk about the deposit flow. The deposit flow is a lot simpler than the withdrawal flow. So here we have a user. The user wants to deposit Ether or maybe ERC20. There are small nuances depending on the choice. The user would interact with the L1 standard bridge contract, which would communicate with the high-level messaging contract L1 cross-domain messenger, which would then communicate with Optimism portal. It actually calls the deposit transaction function on the Optimism portal. And here, a transaction deposited event would be emitted. The sequencer that is listening to events emitted by Optimism portal would not process the event immediately, but it would wait a few minutes for a certain number of blocks to reduce the chances of reorgs. So after the n number of blocks has passed, then it would pack the information into a transaction for execution, and it would go through L2 cross-domain messenger and then L2 standard bridge. So if it was Ether, the user would just receive Ether, but if it was an ERC20 token, then they would receive the bridge version of it. Now let's talk about withdrawals. So withdrawals start, of course, on the layer 2. And there are 3 high-level steps, right? Initiate, prove, and finalize. And then also I've marked asset release on this diagram. So the user would initiate withdrawal on the layer 2 through the L2 standard bridge contract. That would communicate with L2 cross-domain messenger, and then it would go to L2 to L1 message passer. L2 to L1 message passer is the critical contract here on the layer 2, because it is this contract storage route that is used to prove the withdrawal on the L1. The user, after initiating the withdrawal on the layer 2, would need to prove the withdrawal on the layer 1, providing the necessary proofs. So these proofs, the user doesn't need to do this manually. It's handled, abstracted away for them by the UI using an SDK. They would call proof of withdrawal on Optimism portal, and I'll explain this nuance in a bit. And after they prove, they would need to wait for the challenge period, which is set to 7 days. Only after the challenge period has passed and the claim for the L2 state that the withdrawal depends on is not challenged, it's accepted as valid, then they would be able to finalize the withdrawal and get back their asset, whether it's Ether or ERC20 tokens. But now, because OP Stack has permissionless fault proofs available and enabled on OP Mainnet and Inc., the process involves the dispute game mechanism. So actually, when they're proving, they wouldn't be able to do this immediately. Let's see the UI for brid.gg. I don't know how to pronounce this. So number 1, initiate withdrawal. We know that on the layer 2. Wait 1 hour. Proof on Ethereum. This is proof withdrawal on layer 1. Wait the challenge period. And this is finalize withdrawal. What is this wait 1 hour? The reason we need to wait 1 hour is because when you want to withdraw, you need to wait for a dispute game that contains your withdrawal transaction. So let's go on to here. So for simplification, let's assume that 1 hour is equivalent to 100 blocks. And here we have dispute game 0 created for block 100. The user has not initiated withdrawal. And then we have dispute game 1. The claim is for block 200. The user has not initiated withdrawal. And then only in block 230, the user initiated withdrawal. So at this point in time, there is not yet a dispute game that has this user's withdrawal in the L2 to L1 message passer storage. So the user would need to wait for the next dispute game to be created. So dispute game 2 would be for block 300, and of course it would include transactions that were made in block 230. And the reason that this is currently 1 hour is because the proposer has been retrofitted with a new responsibility, which is to create a dispute game every hour, which is the same interval as it was posting output routes before permissionless fault proofs. And so the users can conveniently reference the dispute game that was created by the proposer when they want to prove their withdrawal. Now, of course, technically, the user can also create their own dispute game, but this comes at an extra cost because every time you create a dispute game, you would need to put up a bond, which is currently set to 0.08 WETH. So the proposer, makes the life of users easier, but the downside is that users need to wait for the next dispute game to be created before they can prove their withdrawal on the layer 1. Right, so how is security guaranteed? Our withdrawal flow touched upon this briefly. Essentially, it's the fraud-proof or fault-proof mechanism combined with the challenge period. So the dispute game mechanism, as I mentioned, involves dispute games that contain claims about the L2 state. The claim rests upon the output route claim, which contains the state route and also storage route for the withdrawal transactions. There are two components, off-chain and on-chain. So off-chain, we have OP Challenger, which is responsible for monitoring dispute games that are created. And if there are dispute games with claims that could be invalid, then it would proceed to challenge the dispute game claim. It would liaise with Canon, the fault-proof VM, and Canon can use OP program to emulate execution traces of the EVM. And OP pre-image here is to supply OP program with pre-images if needed. On-chain, we have the dispute game factory, which is responsible for creating new instances of dispute games. Every dispute game would have its own instance. And MIPS here, long story short, emulates the execution of the EVM on the EVM, right? But it would only be emulating one execution trace. It's not going to be the whole block. And the way they arrive at this is through the bisection game, which I will not go into in this video. As I mentioned, every dispute game created as a spam prevention mechanism requires a bond, which is currently set to 0.08 WETH. And that bond is returned to the dispute game creator after the challenge period has passed and their claim has not been successfully challenged. So something that has been talked about as possible for some time, but was not yet real, but now it's real, is using ZK proofs with the OP stack. So OP Succinct is a variation of the OP stack by Succinct in collaboration with OP Labs that uses ZK proofs or validity proofs instead of fault proofs. And the neat thing is that it doesn't require a lot of changes. It actually only requires on-chain one contract to be deployed, and that is ZK L2 output oracle. This is actually a variation of L2 output oracle, which is in use for OP stack chains that are still using a privileged proposer. The difference is that it now will host proofs instead of just the output route. That proof is verified by SP1 verifier contract on chain. This is not deployed by the chain itself. It's deployed by Succinct. And off-chain, the proposer is now the OP Succinct proposer, which is a lightweight client because they're not responsible for generating the proofs, but the proofs are instead obtained from the Succinct proven network. So OP Succinct proposer plays this intermediary role, requesting ZKPs from the proven network and then posting it on-chain. So the neat thing is that the challenge period of 7 days is no longer there, and it's now down to an hour currently for the only chain that's using this. But that 1 hour can be reduced over time to a matter of minutes as performance improves. Something else that we can talk about is censorship resistance. OP stack chain comes with censorship resistance, and this was demonstrated through the recent, at the time of video creation, recent debacle regarding Sonium. So Sonium is Sony's OP stack chain. They censored tokens, some meme coins that infringe upon their copyright at the sequencer level. So what they did was any RPC calls that involve these censored tokens would just not be processed. The sequencer would just ignore it. Dono here from L2B demonstrated how OP stack chains have censorship resistance properties. And the way he did this is through a regular deposit transaction. So this is the same transaction as a asset deposit transaction, but the difference is that instead of depositing assets, we are now wanting to call a contract. So in the transaction, Dono specified the contract for the DEX and also the call data for doing the swap. And he successfully carried out a swap on the L2 through a transaction on the L1. And this took only a matter of minutes. The reason that this was the case is because L1 transactions must be included in the layer 2, because otherwise the calculated state root on the L2 would be invalid. So that's very neat. And this is something that also is accessible via UI. So here on Superbridge, you can see that there's an escape hatch toggle. So this would do a similar thing as to what Dono did, which is allow you to initiate a withdrawal for the layer 2 through a layer 1 transaction. So this prevents sequencers from being able to block you from withdrawing out of the layer 2. That's pretty neat. Now, there have been a number of upgrades to the OP stack in the past. The first one, of course, the major one, Bedrock, which modularizes the stack for the first time and thereby creating the OP stack. Because before that, it was really just a stack that powered Optimism's mainnet. And then we have, in June 2024, the fault proofs upgrade, which launched permissionless fault proofs. There were some security issues that were found, and so the permissionless fault proof system was disabled temporarily. Issues were fixed in the Granite Network upgrade, and now permissionless fault proofs are back live. In terms of what we can look forward to in the future, currently at the time of video creation, there's a small upgrade to the Superchain registry, which is currently a GitHub repo that contains a list of chains and records their superchain status. So this protocol refines the criteria to be included in this registry and how they're evaluated. And also, as part of it, there's a new requirement for chains to be deployed using the new OP contracts manager. The big thing about a superchain is native interoperability. That means superchain chains would be able to seamlessly have assets transferred between them and have native cross-chain messaging from L2 to L2. And it all started actually with just vibes. Initially, there were no specs, but over time, it became more concrete, more tangible. Now we even have the Superchain ERC20 contract standard, but it's not yet functional because that depends on the native interoperability feature, which is still in the works. And also, we of course have the Superchain registry repo, which is the source of truth for Superchain membership. A thing to note and to consider is that Superchain membership means a singular upgrade path. So Superchain chains would be able to vote on upgrades, but then once an upgrade passes voting, then all Superchain chains would undergo that upgrade. Control is released in order for security as well, because it would be a very bad thing if a vulnerability was found and only half of the chains were updated and the other half were not, leaving the door open to attackers. Superchain membership requirements are governed by the OP Collective, and now we have block space charters. The first one being the standard rollup charter, which defines what a standard rollup is. And when a chain is a standard rollup, then it qualifies for Superchain status. And this is all recorded in the Superchain registry. Coming to an end, why use the OP stack? The OP stack is fully open source, MIT licensed. You can swap out any component for any other component that you want. It's battle tested. It's been audited by top firms, and as you've seen, it's gone through things on mainnet that have since been rectified. So you know that there's a high degree of confidence, much better than if you were to create your own stack from scratch. There's the builder network effect now. So instead of just OP Labs working on the OP stack, we also have engineers from base, and that just means more robustness because there's more parties who are treating this as a critical component and contributing to it. And lastly, of course, a chain might want to have access to the superchain ecosystem. That's it. Thank you for watching. I want to give a special shout out to Hashigo, Vex, and Kelvin for helping me understand the OP stack better. I hope that I've done the same for you. Have a good day. Until next time.